Almost 2,000 years ago, the Greek scientist Hero of Alexandria was aware of the tremendous potential of steam, though it was not until about 200 years ago that technology had advanced sufficiently to allow industrial steam boilers to be commonly used. Since that time, the design of steam boilers has been constantly improved, and they are now used in many of today's industries to provide a modern, efficient energy system for process, heating, and power. Because a boiler works under pressure, it is not usually possible to see what is happening inside it. The terms wet steam and carryover are everyday idioms in the steam industry, yet very few people have ever seen these phenomena, and the actual water movement inside a boiler has, until recent years, remained largely a matter of conjecture. As we can only see the water level in the boiler gauge glass, and this is usually quite steady, many people quite reasonably assume that the water in the boiler is almost still and at a fairly constant level. We will demonstrate how two modern fire tube package boilers operate, one designed with an oversized shell and the other of typical modern compact design, and shows the effect of the following: normal operation, feed pump operating with on-off water level control, high steam demand, normal TDS, high TDS. Let us look at a diagram of the first boiler, which we will call Boiler A. Though this is a modern design, the boiler was specifically chosen for demonstration because it has a comparatively large shell for its required output, which gives a gentle boiling action seen in boilers of 20 to 30 years ago. This is a 3-pass boiler. The second boiler, Boiler B, could also be described as a 3-pass design, but in this case the first and second passes take place in a single furnace tube of comparatively large diameter. For this reason, it is known as reverse flame boiler. This particular boiler was selected for demonstration because it is of a very compact design and typical of a modern small industrial boiler. Here, the inside of Boiler A can be seen viewed from the top left burner end of the boiler. Front and rear protection tubes are visible, as well as a horizontal stay brace running from the front to the rear of the boiler. The stay brace is visible at normal water level, unlike Boiler B. With Boiler B, the interior can be clearly seen with the bottom of the boiler manhole visible at center top. Behind this can be seen the low water probe protection tube. The steam nozzle is between the manhole and the protection tube, and though the steam nozzle itself is not visible, the water vapor which forms whenever the feed pump is on can be seen flowing upwards towards this point. Let us first examine both boilers working on a light, steady steam load with a normal TDS level of about 3,000 ppm. Note how even at this low, steady steam generation rate, there is considerable movement of the water and significant variation in its level. We can also see the need for a protection tube to smooth out the fluctuations in boiler levels if we are to have accurate level control. Here we see Boiler B working under similar conditions. The difference is obvious, with far more turbulence and steam bubbles, which, although large, burst quite quickly. We will now reduce the pressure in Boiler B from a normal 115 psi to 50 psi and observe the effect of firing at reduced pressure. Note the high, surging turbulence and large bubbles with water splashing towards the steam nozzle. The appearance of the water surface is typical of a steam boiler working at low pressure. The steam bubbles are larger simply because they are not as highly compressed. When the feed pump switch is on, the first thing we can see is a mist which appears in the steam space as soon as the pump starts and disappears the moment the pump switch is off. The effect is apparent in both boilers. The mist is almost certainly caused by the comparatively low temperature of the feed water, which is approximately 185 degrees Fahrenheit. Most certainly caused by the comparatively low temperature of the feed water, which is approximately 185 degrees Fahrenheit for both boilers. An interesting phenomenon can occur once the boiler feed water pump has turned off. Watch how, after the mist has cleared, the water level continues to rise. In fact, what is happening is that the cooler feed water has temporarily suppressed the boiling rate, and with the burner firing, what we are seeing is the normal steam bubbles reappearing as the boiler resumes full steam production. This effect is a disadvantage of on-off level control and is much less pronounced with modulating control of feed water, where the feed water flow rate gradually alters to match any change in steam demand. A similar effect can be seen in boiler A, though the rise in level is not as pronounced due to the oversized shell. If we now increase the steam demand, the water level will rise. Observe first boiler A. And now, boiler B. This rise in level is caused by the drop in boiler pressure and flashing of the boiler water into steam as the demand increases. The bubbles of steam expand under the reduced pressure, causing a rise in level which is not always apparent in the sight glass or inside the protection tube, both of which contain water without steam bubbles. If the steam demand is increased beyond the limit of the boiler's maximum steam generation rate, the effect can be spectacular as well as potentially dangerous. If water is allowed to carry over with steam and accumulate in the steam main, it can cause severe damage to valves and fittings through water hammer and could even cause injury to personnel. Impurities in the water can also cause contamination of the steam main, control valves, heat exchangers, and steam traps. We have seen how the water level rises in a boiler when the load is increased. This is often referred to as swell. It is, however, not uncommon for a boiler to shut down when overloaded due to the water condition. In order to explain this apparently contradictory phenomena, we will slightly overload boiler B for a short period and observe the effect. Within a few seconds, the water level rises to the extent that water begins to be drawn into the steam takeoff. As soon as the high demand for steam moderates, the water level drops and the low water cutoff turns off the burner. A sustained high steam demand can result in the tripping of the low water and auxiliary low water cutoffs while that demand is still present. In a moment, you will see boiler B being put on load to create a steam demand of 6,600 pounds per hour, which is 15% above its maximum rated output. See what happens only a few seconds after the vent is opened. The level is rising rapidly, and the water starts to be drawn into the steam takeoff. This is water that would normally be carrying over straight into the steam system. Now the water level is so high that it has obscured the camera port, yet the level in the gauge glass is starting to drop. The indicated water level is still dropping, though the viewport is still obscured. The low water alarm has now sounded. Although the level in the boiler is quite obviously too high and carryover is occurring, the water at the top of the boiler consists mainly of steam bubbles, and the level probes, being in the protection tube, is measuring virtually bubble-free water. The sight glass is also giving us a similar indication of the water level. As soon as the burner shuts down, the level of this bubbles-charged water drops very rapidly, so much in fact that it exposes the stay bars in the boiler. Both low and auxiliary low water alarms are now on. The presence of vapor indicates that the feed pump is operating and that normal conditions are being restored. Boiler B was allowed to operate with the TDS control disabled until a TDS of 5,600 ppm was reached. The normal operating TDS for this boiler is 3,000 ppm. We can see immediately that the appearance of the boiler water has changed. The bubbles on the water surface have a foamy, creamy appearance and are much smaller and slower to burst than at normal TDS levels. The surface of the water appears calmer. Even with a normal steam demand, the rise in water that occurs when the feed pump switches off can cause problems. Observe what happens. Within seconds, the water level has risen to the extent that foam is being drawn into the steam nozzle, causing wet steam. Boiler pressure is a fairly normal 115 psi at this point. So even with a moderate steam demand, badly controlled TDS can cause foaming, leading to carryover and wet steam. We have seen the way in which water behaves in steam boilers under normal conditions, high and peak steam demands, and have examined the effect of normal and high TDS. We hope we have also demonstrated just how important it is to have precise, accurate level controls and alarms, as well as providing a system to control the level of total dissolved solids as closely as possible to the boiler manufacturer's recommended level.